Good afternoon. This is Dr. Eidelberg, and today's discussion will cover Introduction to Robotics. We are in Module 1 of the robotic course, and we will open up the reference material of Lecture 1, Introduction to Robotics. The lecture will cover some of the basic policies and regulations for the course, and we will skip that because that is covered in a different presentation. We will also not cover my personal experience with robotics in the first introduction. However, when we go to the second phase of the introduction to robotics, then we will talk a little bit about the definitions, historical overview, market and applications, and the applications will refer to some of my experience in that area. So we will skip the personal section and the course outline and assessment procedures, the laboratory projects. All of that will be covered in a different section, and we'll start with the definition of a robot. So the Robot Institute of America defines a robot a reprogrammable multifunctional manipulator. It's quite general. We see another definition by Google: a machine capable of carrying out a complex series of actions automatically, especially one programmable by a computer. And Webster defines it as a machine that looks like a human being and performs various complex acts of a human being. Which is quite specific. We see over here several illustrations of different types of robots. We see Asimo, a robot made by Honda, which indeed looks like the Webster definition, quite impressive. We see military robots that look more like a mule, which could actually be transforming heavy loads in difficult terrain. And a more common industrial robot, as the one that we'll be focusing in, is the manipulator, which is reprogrammable and used extensively in manufacturing processes. We see over here different types of robot. Primarily what we see over here is an articulating robot. We'll learn more about that when we talk about kinematics, and also Cartesian robots, XYZ, which are transforming parts and tools at the end of arm. We start by looking at the trends in robotics with the first industrial revolution, where mechanization and water power and steam power actually allowed the industry to automate many of its processes. Then the second industrial revolution was identified earlier in the last century with mass production of automotive vehicle and assembly lines which are based on electrical power. Then the third industrial revolution, where computers in the middle of the last century entered into the manufacturing process and started the entire process of automated, flexible automation, like a robot, which could be reprogrammable to do different tasks at different times. And now we're in a fourth industrial revolution, which is called Industry 4. And we see that robots are interconnected to many other peripheral equipments through various types of communication, through lines or wireless, and the entire system, which is defined as Internet of Things, is becoming the essence of today's technology, manufacturing technology. When you see the environment for the next decade in Industry 4, the highlight items are innovations, modeling of systems, simulating systems before any expenditures are made in building them, printing, 3D printing of ideas which are on engineers' desks, a lot of programming of various computerized machines, communications through Ethernet, through field buses, and sensings of various types. The process of integrating all of these activities in Industry 4 can be segmentized into vertical networking integration, where smart factories are connected vertically to customer-specific production needs, and automation, autonomous organization of manufacturing facilities, including maintenance and supplies with smart sensors and monitoring the machine for quality of flow. So these are the vertical integration of various intelligent components of the manufacturing system. And we have horizontal integration within the corporation of marketing, warehousing, supply chain, monitoring, and continuous flow of material and product within the corporation horizontally. Then engineering supports it all with simulation, design, printing, manufacturing, testing, integration, and operation. And then it all goes into the artificial intelligence, which is the driving force in robotics, with continuous improvement, smart sensors, new materials, Internet of Things, communications of various types of technological singularity. Technological singularity basically means that the trend of advance in technology is proceeding so rapidly such that the solutions to problems may be before the problems actually arrive. And what it means to us is that with such a rapid progress of technology and the so-called 5-year half-life of any skill set that we learn today, it means that we have to actually have the attitude of continuous learning. We see over here two major types of robot types and markets. These are so-called Cartesian robots, which move in XYZ coordinate system, and these are so-called articulating robots that moves in pitch yaw roll and various joint rotating joints in order to position the part in space. Cartesian robots are mostly being used in semiconductors, manufacturing processes, in electronics, assembly, machine tool, and pharmaceutical. And they're pretty small and precise and extremely high performance. It can move fast and have a very high dynamic precision. The articulating robot, on the other hand, they cover a larger space. They're mainly used in aerospace, in automotive manufacturing, food and beverage, and general automation for pick and place. They're large and provide coarse positioning. When we say precise, we mean on the order of microns. When we say coarse, we mean on orders of millimeters or fraction of a millimeter. Over here we see some of my examples of my involvement in robotics. We see that this is a cryogenic chamber where a robot is being used, experimented in order to transform medical parts from one point to another, and different environmental conditions like thermal, shock and vibration, magnetic, EMI, RFI, radio frequency, electromagnetic interference, humidity, and cleanliness are environments that human operators many times cannot work properly, and that's where robots are being used, and that's where engineers develop the technology in order to operate the robots in these environments. Here's another example of my patent with some of my colleagues at Festa Corporation, where engineers use existing robots which are purchased, but the gripper, the end of arm tool, is customized for specific application. We see over here 64 pipettes, and they are being placed at certain pitch, and the liquid from these tubes is being picked by the pipettes and being placed on biocells, biochips at a different pitch. Therefore, they have to be picked at once and then at once be positioned on a biochip at a different pitch. So in order to make the process a little bit optimized in throughput, we developed this variable pitch gripper, and engineers use quite a bit of their time to adopt custom grippers to standard robots that they buy. Here's an example which uses another patent pending of mine in cooperation with Goodyear. You see over here the application, and there is a next generation tire manufacturing where we have filament which comes in through the machine over here, and a robot over here which was customized with Parker Hannifin engineers is doing a complex motion over here to wind the filament soaked with liquid rubber on the tire and let the tire have extensive improvement in its life. This is another example of using standard equipment in order to assemble a custom robot. Over here, this is another patent which is pending, which I've done with Festo. You can see here the video that shows and demonstrates the process. This is a sales engineer which is describing the application in automotive industry. The cars come in and they use body parts. Different body parts come in on different type of parts, and the gripper over here is customized by us with my own patent with the support of the engineers, and this gripper allows to adapt the pins that pick up the body part in order to adjust and save the time. It takes about 7 seconds to change the tool, and with this variable pitch gripper, the 7 seconds is being saved. This is a design engineer that describes over here the patent of using standard slides and stages in order to assemble a variable pitch gripper. You see over here how this element is being placed on a robot, and the pin at the end could be variably changed in order to fit the desired body part of the automotive. So this is in itself a gripper. You see over here it's mounted at the end of arm tool, which is a Cartesian robot on itself. So you may vision it as a miniature robot carried by a more larger robot. So this pretty much is the description of this particular video. To continue with our discussion, we see over here another application. This is a tripod. We service over here cookies on a food manufacturer process which needed to grip those cookies at very high speed. So here's an example of engineers that work in robotics, not so much in designing and developing the robot itself, as much as designing and developing the end-of-arm gripper. So this is an example where an engineer, in this case myself, went to Home Depot, buy a small painting sponge, place it as on a printed, 3D printed device, and could prove the concept of gripping these biscuits that are moving fast on the conveyor belt without damaging them. And another example over here shows a Cartesian robot where the customer many times purchase the individual stages and assemble the robot, the Cartesian robot themselves. And in such case, when the customer may not be careful in aligning the two stages of the so-called gantry, then when the x-axis moves, there may be a convergence between the two rails, and the pucks, the slides over here, are going to increase the friction, and that friction may either stop the machine or cause damage to the ball bearing rails. So the development here was to construct for that particular gantry a component which will be providing a give in a direction where we do not need the stiffness, yet maintain the stiffness in the other directions where we need stiff support and high precision. This is an example of a finite element analysis that engineers are doing. Again, this is my invention where we have here a device that is very stiff in the direction of motion, but allows a little bit rotation. With this rotation, it's going to be rotating about this point, and with this 4-bar linkage, allows also displacement in this direction, but it is very stiff in the direction of motion. These are typical jobs that engineers do in automation. Here's another robot that does life science testing. And this is an article which I wrote from machine design with my colleagues at Festo Corporation. It's using an H gantry, a small gantry, over here within a small chamber to pick and place autonomously fluids from one container to another and do some analysis such as DNA analysis. Many of the analysis that engineers do in robotics are supported by tools. Here's an example of a tool which I wrote for servo control. You click on this element, you can train yourself simply by clicking on example. It fills in the data, and then you run it and you come up with, in this particular case, with step response in time domain and also frequency response. You can also change the parameters, the PID parameters, or the machine parameters like mass stiffness and damping in order to receive an optimum servo performance. The other examples that we have over here are tools that, again, I developed these ones. The same process, you click on that and it allows you to calculate automatically the precision at the end of arm when you have many links and joints that could contribute to the inaccuracy. So you click on that, you put some basic variables in the yellow boxes which describe the system, and then click run, and you get the accuracy result in XYZ. Here's another example for robotic motor and actuator sizing. In this course, we'll do some experiment with that and also exercises, and this is an example of how to size for a given motion profile, motor and actuator. In this particular case, it's a ball screw actuator. Typical problems that engineers do in the robotic arena. Here's an example for the same video that we saw, how to actually design the operating system where we have here the robot and the end of arm tool that we saw earlier, and we could optimize the position of the robot when it does some welding process on a different body part on a platform over here, which is called a geo plate. So this is another tool that helps the customer to do that, and engineers in our business typically involved in this. Here's another example that shows a complete automation line. It is using visual components, a simulating system, and it's part of a virtual reality system where the customer can actually walk through the manufacturing process and see the details of each one of these automation components that is being done. And this is a cobot operation, a collaborative process of human operator and a robot. This was done in collaboration with Visual Components and Festo Corporation. This concludes our presentation for today, and we will continue with other subjects of the course in upcoming lectures. Thank you.